You sure? So we're gonna hit this in kind of batches. I figured the first one, I think this is probably the easiest of the ones. So we still have to factor cubes, we have to factor lookalikes, and then we have to factor by grouping. I feel like this one's probably the easiest just because it's all formula based. Um, so what we're doing today is 4/3/23. Ooh, the date is yellow. That's new and exciting. We are factoring sums and differences of cubes. So I don't know if you want to write this part down. I do this a lot where like I'm not sure if I want it to be in your notes or not because I worry that this would confuse you if you were to look back at it. But something that you've factored before is called a difference of squares. So I'm going to show you an example of that. And this again is not really part of today's lesson. I'm just merely trying to remind you of something that you've learned in the past. So this is a quadratic, and if you were to factor this, you would factor this into x plus 10 times x minus 10. Trust you remember that, right? And likewise, if I gave you like x squared minus 4, that factors into x plus 2 times x minus 2, right? I mean, I could keep going. We could make these even more complex. We could do like 4x squared minus 121 y squared. And it still, by definition, is a difference of two squares. And so to factor it down, it's just predictably simple. I would just take the square root of 4x squared and put it there and there. And then I would take the square root of 121y squared, which is 11y, and put it there and there. And then I'd stick a plus and one and a minus in the other. So that's kind of more algebra 1-y level factoring. That's just called a difference of two squares. And I just don't want you to get it confused with what we're going to do today. Again, those are called squares. Important. So today we're going to be factoring cubes, not squares, but cubes. So as an example, I have I have six examples for the notes. If you want more, I can give you more. Just let me know when we're done, how you feel. If you're someone who gets math anxiety, like just a little bit of newness causes you to go off the deep end, you might be in for an interesting little ride here. You have to have a lot of faith in the formula. All right. Anyways, this is called a sum of cubes. So from now on, when we identify something like this, I'm not going to write this down every time, but it is called a sum of cubes. It's obviously a sum because there's a plus sign in the middle, and the things are called cubes because they're the answers to something cubed. We agree, I hope, that 125 is a cube, x cubed is a cube, and 27 is a cube, right? So having said that, we're going to take a look at this first term right here and ask ourselves, what would you have to cube to make 125x cubed? 5x, right? So we're going to call that a. So our a value in this problem is going to be 5x. And what would you have to cube to make 27? So our b value is 3. Now, there's a formula for this because it's not like I can teach factoring quadratics using common sense. Like I can construct it with you, and for the most part, you can kind of get right in the moment and make sense. Like when we factor something into 2x plus 5 times 3x minus 7, it feels and makes sense. Like you get the whole, it works. This isn't like that at all. This is very non-intuitive. So I'm going to give you the formula for this. And there are going to be two formulas today. One is for a sum of cubes, and then the other one obviously will be for a difference of cubes. So here's your sum of cubes formula. If you have a cubed plus b cubed, then it factors down into a plus b times a squared minus ab plus b squared. I'll say this for the first of probably 100 times that I'll say this. Think of it as short set, long set. So when we factor cubes, we're going to say short set, long set. And what really becomes the deal breaker for a lot of people is where does that pesky minus sign go? You'll notice that there is just one minus. There's a plus and another plus later, but then just that one pesky minus. And so I'm not ready yet to talk to you about like the shortcut or how to memorize it. For now, I would just tell you, you really should write down that blue formula. And again, that is the formula for how we factor half of today's problems, sums of cubes. Bless you. Is that a sneeze? Oh, well, bless you anyways. In case you sneeze later, I've given you a preemptive bless you. You're welcome. Good, good. So here's what this is going to look like. Whenever I factor cubes, I'm going to build short set, long set. Before I even get started, I like to build my short set, long set. And now I'm going to just very faithfully apply the factoring formula, which says in the first set to do a plus b. So what is my short set going to look like? 5x plus 3. It's quite literally a plus b. I don't think I have any professionally, like legally allowable words to express to you how important that red box is. Writing down what A and B, like explicitly writing down what A and B are, is huge. It's everything. So when we begin a problem, we want to identify them so that when we go to plug into the little formula, we're like, I got everything I need. Now, at the beginning of long set is going to go a squared. And what is a squared? Perfect, 25x squared. And in the center of long set is going to go minus a times b. What is a times b? Very good. And then at the back of long set is going to go plus b squared, which is, and with that, you are done. Again, that's not the kind of thing. I feel like teaching, like I just got done doing this in Algebra 1, teaching kids how to factor quadratic trinomials is just, you can flow it, like you can see why all the things go where they go. This is not like that. And if you didn't buy it, like you could actually go through and multiply this back out and do the 6 math problem distribution and say, wow, I'll be darned, it actually comes out to 125x cubed plus 27. But that's just basically how you factor a sum of cubes. Okay. You're going to want to ask the following question, and I just thought I would get in the way of this, but you'll ask it again at some point, and I'll answer it again. It's okay. You're going to want to ask this. Can I factor that? What I just underlined in green. And the answer is unequivocally no. The only exception will be if later in this lesson, if you miss the part about pulling out a GCF, then you will be able to factor further. Okay, but if when the GCF comes, if you heed my advice and always pull the GCF out early, which again doesn't apply to this problem, the green thing, the long set and the short set are never going to be able to go factor more. That's the fun thing about short set, long set is you know you do one step and you're done, provided that you did things right, like for the setup. Okay. All right, so that's how you factor a sum of cubes. Let's do another problem. This one, as you probably would guess, is going to be a difference of cubes. So 27 x cubed minus 64. What is a? 3x. Remember when it's a multi-part term like that, that you have to cube root both the number part as well as the variable part. So 3x is the cube root of 27x cubed. And what is b? and it is just 4. I appreciate the sentiment of saying -4, but this other formula that I'm going to give you will already have taken into consideration the fact that there's a minus sign in the middle. So when naming your a and b, don't take that middle sign into account. All right, so a is 3x, b is 4. Any questions about how we're getting those numbers? All right, so the formula for a, by the way, this again, I guess I'll just write it down and make it official. This is, of course, called a difference of cubes. I mean, it stands to reason. It's a difference because there's a minus sign in the middle. It's a sum and it's a plus sign in the middle. And so for a difference of cubes, we have another formula, and it says this. It says that if you have a cubed minus b cubed, factors predictably into short set, long set. Your first set is a minus b, and your second set is a squared plus ab plus b squared. So it looks familiar, right? I was going to ask you a dumb question. Say, does that look familiar? Of course it looks familiar. It's very similar to the formula for the sum of cubes. What do you notice? One little nuancey difference. Who moved? Yeah, your minus just jumped, man. So like in your sum of cubes formula, the minus was here where that little yellow arrow is pointing. But in the difference formula, your minus just jumps and goes over to here and switches places with that other plus sign. I'll tell you this, that the way I always memorize it is whatever the sign is in my original problem. So like if your original is a difference, then your short set will look that way. Your short set will always mimic the original expression. Does that make sense? Okay. So having said that, we now have the other formula for the day, and it's just really a matter of, it's pretty hard to think of messing it up from this point because just plugging stuff in, right? Like I got the template, I just pop in things and call it a day. So when I factor this down, I'm going to factor it into short set, long set. What's going to go in my short set? Yeah, a minus b, 3x minus 4. What's going to go in my long set? 9x squared is my a squared. Good job. And then remember, plus from here on out. Plus 12x plus. Done. It's not hard, right? Very formula based. It's like make sure you have your formulas. And as long as you remember that short set is AB and long set is a squared AB b squared, and you just remember where to place the 1 minus, you're in like Flint. So I have 4 more examples, and you might wonder, like, do we really need 4 more? Well, I don't know. Let's find out. What do you notice? Say again? Yeah, it's there. These aren't cubes. So what happens is what you're looking for is often buried underneath like a layer. So the layer is called the GCF, and get used to this for the next couple of weeks. Please get used to this, that the math problem that I really want you to factor is not visible at the surface. We can't get to it and factor it until we pull off, it's like peeling off a layer of an onion. So what I have to do is I have to look at my 2 terms. There is no conversation right now about who is A and who is B. That doesn't exist yet. What does exist is this question. What can you pull out of that and that? X. So from this point on, our new normal is look for the GCF, look for the GCF, because the GCF is going to be a deal breaker if I miss it. It stands for greatest common factor. It's the most, like the biggest amount of X or number or whatever you can get out of both of the terms. I sometimes refer to it as like the Gary Charles Franklin or something. We're going to talk a lot about GCF because quite frankly, it'll primarily be the thing that causes people to go, I don't get this, or how come I didn't get this one? It's usually that you missed the GCF. So when you look at the two terms that I have circled in red, you realize that they can both be divided by x. And so what I'm going to do is I'm going to pull that x out, and I'm going to rebuild the math problem. So what is 216x to the fourth if I remove one of his x's? Nice. And what is 125x if I remove his x? Good. So pulling out a GCF is just really doing the distributive property backwards. It's undistributing the x. And then you expose, after you peel that layer off, you expose the actual math problem that I wanted us to do, which is in the parentheses. So we get to ignore the x now for the next couple of minutes, and let's answer some questions. What is A? It is 6x. The cube root of 216 is 6, and the cube root of x cubed is x. And what is B? Good. And I'll say it again, at this point, I don't understand for the life of me how you could miss this. It does happen, but it's just, it always kind of goes above my head. Like, how did you do that? Like, we have a formula. We're just going to pop things into their little places and move on our way. So our final answer is going to look like this: x times short set times long set. That GCF is just going to hang around like a bad cold. Like, we no longer have to consider it or worry about it. It's just that we have to keep it present and accounted for. So what's going to go in my short set? Definitely A plus B, 6x plus 5. What's going to go in my long set? Yep. After 36? Minus. Good for you guys. You got to get that minus in there. Plus 25, and that is done. Still good? Okay. 3 down, 3 to go. Our next math problem is 24 minus 81x cubed. You notice right away, of course, that 24 is not a cube and 81 is not a cube. So Brady, what are you thinking? Sure. You just leave it there. When we talk about factoring, the act of factoring is merely the act of breaking something into as many multiplicative pieces as we can so that we can solve equations or cancel things out. So this is the final answer. We just leave it there until later on we have a reason to do something. Does that make any sense at all? Okay. It's not much exciting about factoring. It's just the act of doing something that will enable us to solve other problems. Factoring just becomes like a tool. So for this next problem, what do you notice about 24 and 81? Yeah, they can't be cube rooted. So we're looking clearly in a case like this for a GCF, right? Please get used to this. Exactly half the problems on today's assignment have GCFs. And if you don't see them, you'll just hit a wall. Like, it didn't happen. So, so what is the GCF? What can 24 and 81 both be divided by? Yeah. Certainly not 2. 3, right? It's okay, Bryn. So if I divide them both by 3, I'm going to take that GCF and I'm going to pull it out front, and then I'm going to rebuild the problem. People that try to skip the rebuilding the problem step, they generally kind of suck at this. So there's no contest. There's no flexing on the world. Look how much I can skip steps. Just take your time. What is 24 when you divide him by 3? He is 8. And what is 81 when you divide him by 3? Yes. So again, what happened is the math problem that someone wanted us to do was 8 minus 27x cubed, but they essentially buried it under a layer of times 3. And it's our job to undo that layer by dividing out the 3 to expose the math problem. when we see it like this, what is A? It is 2. What is B? Good. And again, please disagree if you want. I just can't find any good reasons why you could possibly miss it from this point on. So here it goes. Final answer is going to be 3 times short set times long set. The GCF, again, just hangs around. Don't throw it away. Don't think it's like, oh, I divided it out. It's gone. No, you didn't divide it away. You just pulled it out. It's still there. What's short set going to be? 2 minus 3x, right. And then what's long set going to start with? 4 plus 6x. Another one bites the dust, right? 2 more. So 5,324x to the 5th minus 2,048x squared. Yeah, what a mess. So clearly we're looking at a GCF situation here. So you want to have your resources handy and you want to know who your cubes are. So remember, you have a piece of paper somewhere that has all your cubes listed. If you don't have it, I mean, you've had it at one point, but if you manage somehow to lose it, there's more here. And at the bottom of this is a list of numbers that are cube rootable. First thing we notice is, of course, that 5324 and 2048 are not, they don't make the cut. They're not on that list. So what you do is you start just chipping away at the stone and you ask yourself, what can I divide both numbers by? 2. What else? 4. Let's try dividing them both by 4. This is a really good day to have a calculator because as I start screwing around with numbers, I kind of want to be able to divide quickly without messing up. And calculators never mess up. So I'm going to take 5,324 and I'm going to divide it by 4. Does the number that I get, does 1,331, is it a good one? Is it cube rootable? Is it on our list? So I guess we have to go bigger, huh? So let's keep dividing by other things. What else do you think? Maybe 53, 8? You want to try 8? So let's do 5324 divided by 8. Doesn't work. What else do you want to try? 7. That's an interesting selection. That doesn't work. What else? If you'd like to know, say it again. 22. That gives us 242. So you see how we're kind of shooting in the dark here. Here's a pro tip. If you look on that piece of paper, I'm going to write down a list of numbers over here that I care about. This is a good time for you to absorb this because you're right in the moment. This is a perfect time to hear this. I don't want to divide by 2 and 3 and 4. I want to divide by 8. And I want to divide by 27. And I want to divide by 64. And I want to divide by not 125. That would be stupid because the numbers end in 4 and 8. And even 27 might be stupid, but I'm not really sure. 216. Where am I getting these numbers from? They're cubes. And if I can divide by a cube, that's progress because then I'm breaking it down in a productive manner. Like dividing by 4 did us no good, right? But that's because 4 was a useless pile of crap. So let's try dividing specifically by those things. Did you just say 216? That doesn't work. How about by 64? Nope. What else do we have? No, I'm not actually convinced that any of them work. What about what's after 216? Is it 343? 512 doesn't work either. 729, does it work? God, I wonder if I wrote down a bad problem. I must have. In my defense, it was early. Do you guys know how to do cube roots on your calculators? Of course you do, because we did that unit where you had to do roots. Will you guys do me a solid and figure out the cube root of 1,331? Yeah, so it actually turns out that we do want to divide these both by 4. It turned out that actually was not unproductive. So if you take both of these numbers and divide them both by 4. So if I pull out a 4, and by the way, that isn't necessarily maybe it is my GCF, but it's definitely a UCF. That stands for, I just made that up. That's a useful common factor. If we divide these both by 4, what else can we divide them both by? What? X squared. Very good, Bryn. They both have x squared to give. So we pulled out a 4, and we also pulled out a pair of x's. And now we're going to rebuild to see what's left. So what is 5324 divided by 4? Nice. X to the third, because I divided out 2 of his x's. And what's 2048 divided by 512? So I think the reason that we missed 1331 is because your cube root list stopped at 1,000, right? Yeah. So maybe right now, if you have that piece of paper out, you could add on to that list. Every time you find a new one, you should add it on. So the last one that's on your list says this, that the cube root of 1,000 equals 10. Well, now we can add a new guy so that we don't have to go through that again. The cube root of 1,331 equals 11. Because now that we know how to do roots on our calculator from that compound interest unit, then we can find whatever we need. So let's get to it. Kind of eating up a lot of the hour here today. What is A? 11x. Good job, you guys. And what's B? Good job. And so again, the hard part of the problem, I would say, is officially over. It's time to build our answer. And our answer will look like this. 4x squared times short set times long set. You just kind of do it the same every time. What's going to go in short set? And what's going to go in long set? Careful. 121 x squared. You're fine. Plus 88x plus 64. Done. So good. All right, one more. Promise. Last one. Ooh, I need a new page. Step 1, find that GCF or that UCF, that useful common factor. It's going to be the GCF, by the way. You should be actively right now dividing by things like 8 and 27 and 64 and 125, the numbers that we're interested in. Don't make a random scramble of it. Divide out the cubes and see what happens. Brady, what'd you find, bud?
3,000. The other one is.
It's not. Okay. I don't know this because again I never worked this backwards this morning, but I like the 125 just because both numbers end in 5 and 0. So did you try dividing by? It doesn't work either. Okay. Hey, what if we just divide by 5? There's a thought. What'd you what'd you get? Ooh. So you're telling me if I divide both of these numbers by 5, and what else can I pull out while I'm here? Pull out an X. Let's see what it rebuilds to make. I think I like where this is headed. Brooklyn, you said the first one comes out to 729.
Yeah.
I love that. And the other one comes out to 512. Execute. Nice job. Good find. So again, you just tinker with that GCF idea until you find something that's rootable, which in this case, how nice that both numbers that pop out are on our list. And so the GCF is generally a pretty tough part for a lot of us. What is A? Is 9. Yeah, what's B? Good job. And again, we're home free from here, right? Impossible to mess up now. Here we go. 5x times short set times long set. Over and over again. What's going to go in short set? What's going to go in long set? 81 minus 72x. There you go. And that, my friends, is how you factor sums and differences of cubes. I'm going to hand out the worksheet. I'm assuming that we'll be in school tomorrow. If we're not, my Canvas assignment will be continue working on assignment number 24. So my assumption is that once you get this in your hands today at 9:44, it goes into your notebook, and that your notebook will, of course, be at home with you so that you can work on this. If we're stranded at home tomorrow, which again, I have no idea.